So I want to talk a little bit today about how materials influence the magnetic fields they're placed in. And this is a very, very rich and deep field to get into. So all I'm really looking for here is a sort of superficial descriptive understanding so that when you start discussing these things, you'll know how to describe paramagnetic and diamagnetic and ferromagnetic. Not necessarily anything mathematical here, although I will walk through some math just to get us to where we need to be. I'm going to start off just by looking at a hydrogen atom. So imagine that hydrogen atom sitting there, a proton in the middle and an electron zipping around the outside edge. It's going around with a Bohr radius of 0.5 angstroms. And because of that, I can think of that as having a velocity in this orbit, and this is a very classical description. Quantum mechanics would have us do this a little differently. But if I think about the velocity going around, I can calculate the velocity based on the idea that the centripetal force, mv squared over r, is the Coulomb force, the kqq over r squared, where the q's in this case are both e for the proton and the electron. I can solve this for what that v might be. It's e times the square root of k over mr. The e, the k, the m, and the r are all well known. The r in this case is the Bohr radius for a hydrogen atom, 0.529 angstroms, or 0.529 times 10 to the minus 10 meters. And when I plug all those numbers in, what I get is a rather large velocity here for that electron zipping around this circle, 2 times 10 to the 6 or so meters per second. Now what I'm going to do with that is stop and think about what that means is that electron is zipping around this circle with a period that is actually rather high. If I take that 2 pi r divided by v, I can calculate the period of one orbit is about 1.52 times 10 to the minus 16 seconds. So it's going around rather rapidly. It's a very small circle. If I think about that now, I can look at this atom as having a magnetic dipole moment. It's a current loop. The electron going around the orbit is just like current going around a circle. The current is going to be measured in terms of the charge divided by the time it takes to go around. Now I know this is a single point charge, but if you kind of smear it out, if you will, and imagine it as being stretched out around the whole circle, it makes a little more sense. One other thing that's a little troublesome here is the electron is negative, so the current actually goes the opposite direction to the velocity of the electron orbit, so we'll have to keep track of that in a second. In any case, the current is E divided by T, and I just solved for what T was a second ago. I'm going to go ahead and put it in as V over 2 pi r, so that I have I is equal to E times V over 2 pi r. Plugging in some numbers for that, I can calculate the current is equal to about 1 milliamp, which doesn't sound that impressive, but on the other hand, it's a single electron we're talking about here. That's kind of cool. In any case, that's the current, and if that's the current, then I can think of this as being a little magnetic dipole where I have a current times an area. The area in this case is the area defined by that circle, the orbit of the electron, which is pi r squared. And therefore, the magnetic dipole moment of this electron orbiting the atom here is 1/2 of eV times r, or 9.28 times 10 to the minus 24 amperes times meters squared. This is what's known as a Bohr magneton, and it's the magnetic moment of a single electron orbiting an atom. Now, as it is, an atom that has multiple electrons, each one of those is going to add to it. So the total magnetic dipole moment of an atom is a little more complicated thing to figure out, but at least we've got an order of magnitude here of about 10 to the minus 24 or so ampere meter squared for what the magnetic dipole moment is. Now, the reason this is important is because I want to stop and think for a second about the fact that this creates a rather large magnetic field. That magnetic field at the center where the nucleus is, where the proton is in this case, is going to be mu naught times I over 2r, which is about 12.5 Tesla. That's pretty big compared to what we can make in typical situations here on Earth. So we've got a large magnetic field there. But I can come along and hit this atom with an external magnetic field. If I say, for instance, throw a magnetic field onto this thing that points into the screen, so the field is pointing away from you, keep in mind the current that we had before was going counterclockwise, so therefore that magnetic field of 12.5 Teslas we talked about was pointing out of the screen. So now what I'm doing is giving it a magnetic field opposite to the one it's creating, and what that magnetic field is going to do is exert a force on the electron. Remember, the centripetal force was equal to the Coulomb force before, but now if I do a QV cross B on that electron, remember the electron is negative, so I have V cross B pointing toward the left, but then the negative turning it back around so that the force on the electron is actually toward the right. I gain a little bit more centripetal force there. I have an EVB adding to the centripetal force, and therefore the speed of this electron as it orbits is going to increase. And if the speed of the electron in its orbit increases, that means the effective current increases. It's going around carrying charge more rapidly. And if the current increases, then the magnetic field of the atom increases. That 12.5 Tesla gets a little bit larger. But what this means is that 12.5 Tesla was in the opposite direction to my external field. So if I combine those two, the total magnetic field is a little bit less than the external field that I'm applying. In other words, the atom has the effect of fighting against my external field, and this is what's known as diamagnetism. This is common to all atoms, although it's only going to be specifically the case where I have certain types of atoms, because I also need to think about the electron itself. Now let me talk about that for just a second. The electron itself actually has a spin as well. How this actually happens is a little mysterious, but I'll just say it's something we have observed before, and it's well known. It comes up in quantum mechanics, but if the electrons spin, the kind of interesting thing about it is comparable in size to the spin, the dipole moment that the atom itself has. In other words, this electron is sitting there with a dipole moment, just like the atom's dipole moment, but the difference is the electron dipole moment is going to try to get together with this external field. So what will happen is it will add to the field that I'm applying. The atom fights against it, and in some cases what happens is the electron's addition to the field is enough to make up for the atom's subtraction from the field, and therefore I do get an external field being sort of boosted by this electron effect. Now, this is going to happen when I have electrons that don't have paired partners. Remember from chemistry, the electron spins up and down are what give you the Pauli exclusion principle. And if I have a single electron without a partner, it'll have a spin up and it can add to the field. If it has a partner, if I've got an even number of electrons, for instance, then it'll also be another one that has spin down, and therefore I won't get the addition because the two will cancel each other out. A little complicated, but the point being that I can get a case where the atoms, the electrons in the atoms actually add to the field ever so slightly. Both these effects, paramagnetism and diamagnetism, are actually pretty weak though, and aren't something you'll run into terribly frequently in your day-to-day life. The one you do see, though, is when I get a bunch of these unpaired spins, these single electrons that have a mind of their own and add to the field, and they all work together. They'll form what are known as domains, so they talk to each other, and all those electrons in a certain region of a piece of metal will kind of get together and form spins that point in a certain direction. And in general, this would be randomly oriented. But what happens here is if I come along and apply an external field, I can get all these guys to line up in one way, and therefore I have the entire piece of material with a large amount of spin pointing one direction, and therefore I get a huge boost to the external field. This is what's known as ferromagnetism. This can multiply the effect of the external field by factors of 1,000. Now, the other interesting thing about this, though, is when I take away the external field, these spins don't necessarily reset themselves. They'll scramble just a little bit, but that sort of preferred orientation will stay behind. It's an effect called hysteresis. It's a memory of past history here that allows me to take a piece of ferromagnetic material, such as iron or nickel, stick it in a magnetic field so that I pull all those spins in one direction, then remove the magnetic field, and the material stays magnetized. It keeps a north and south orientation to it. And this is the way most bar magnets you've probably played with are made. They're chunks of ferromagnetic material that are pulled by placing them in a strong magnetic field, and therefore remember that field strength, and remember to have their spins all oriented that way so that they themselves are magnets after the field is removed.